Okay, today we will see some interesting property of point processes. And this property about is characterization. On the previous uh, lectures, we saw that if we know the so-called finite dimensional distribution of a point process, then we know the distribution of a point process itself. But it turns out that for one class of a point process, we can give much more simpler characterization. And the class of a point process that we will consider today is so-called simple point processes, and it turns out that for a simple point processes we can characterize them in much more simple case. So let's give the definition of a simple point process, and the intuition of it that for simple point process there can be only one point in the one position. So what do I mean? That if we have the space X, then each point can have mass 0 or 1. So we have or we do not have a point of a point process in specific position. So how we can give the strict definition? So we will say just that arbitrary measure mu, measure mu, which is of class of, as we defined, of measures of class n. So that means that we consider measures that can be represented as a sum of finite integer valued measures. And we say that such a measure is simple. We say it to be simple if the measure of one point subset cannot be bigger than 1. So it's 0 or 1 for all x's. So such measure is simple. So for example, when we considered a point process of the form, such form, let it be not a random but some fixed points where xi does not equal to x yod, then eta is a simple measure. Then eta is simple. And we will say that a point process is simple if with probability 1 we have a simple measure. So this will be another definition that now about a point process. Point process is said to be simple if the probability a point process eta, I will specify here, that So we know that eta is a random measure, so we have some dependence on omega of the probability space. So I just write that eta is a simple measure with probability 1. So this is a simple definition. So we can give the example of such simple point process. If I take the space x just is equal to 0, 1, and I take m uniformly distributed random variables, independent, uniform distributed on 0, 1 random variables, then a point process of the form I from 1 to m is equal to delta measure at these random points is a simple point process. Why is it so? So the main question is that these points cannot be equal with probability 1. Indeed, so the probability that eta is simple means that the probability that x I does not equal to x yod for I not equal yod, I yod from 1 to m. So this is not hard to check, so please do this. So I will write this for exercise. Please check this, that such probability is equal to 1. So we cannot have, so here you should use a joint distribution of m independent uniformly distributed random variables. So this is an example of a simple point process, but here the most important that we take specific distribution of random variables x. So they are uniformly distributed random variables. So let's consider example when the point process has the same form, but it is not a simple point process. So I can construct it in the same way. So I consider my space x is equal to 0, 1. But now points x, I from 1 to m, so they can be independent random variables with distribution. So I just take x I is equal to 0 or 1 with probability 1/2. Then the point process eta 1, which I defined as the same form x I here from 1 to m. Then this is not a simple point process. The one is not a simple point process. Why is it so? Because if we have, let me write this, for m is for bigger than 1, because we have the probability which is not equal to 0, that eta 1 of point 0 can be bigger than 1 with non-zero probability, right? So this means that it's very simple to imagine here. So we have only 2 points, only 2 heavy points, right? And here we have some number of points k, and here m minus k. So we cannot have at these points only 0 or 1. So it's now we can understand that for to guarantee that a simple point that a point process is simple, we should know the distribution of the random points from which we form a point process. And of course, for a simple point process, we know a little bit more. Let's see the difference between simple and non-simple point process. So the main difference between a simple point process that will allow us to give a quite simple characterization of its distribution is that for a simple point process, to know its distribution, we should know only positions of heavy points. So we should know the positions of a heavy point, because here we have the mass 0 or 1. But this is for simple. Here only 0 for 1. But for non-simple point process, we should know not only the position of random points, but we should know the so-called mass of a point. So we can have here bigger mass or smaller. So it's not enough to know the distribution of heavy points itself. So I write it for simple point of process. It is enough to know only positions of heavy points. And this leads to the following idea. Instead to find out the distributions or positions of a point process, of a point itself, we can consider so-called avoidance sets. So what do I mean? If I will know the probability that in some subset A I have no any point, then if I know such probabilities for every subset, then I will know the distribution of the points itself. So this is the main idea of the of the Renyi theorem. And Renyi, first he proved the theorem for a Poisson point process, and he said that it's enough to know the so-called avoidance probability. Avoid probability of the form that probability that point process at from some subset is equal to 0. So he says that if we know such probabilities for every subset B, then if we have a simple point process, then we know the distribution of Poisson point process. So we can characterize a distribution of a point process, of a simple point process here. This is important in terms of this avoidance probabilities. So Renyi idea was that we can characterize distribution of a point process for simple point process using this by these probabilities. So as you see, that this is very simple function, a very simple probability. For every, let's say, Borel subsets. So he proved it first for simple point, for simple Poisson process, and then he generalized it for all simple point processes. So let us understand this idea. Why is this true? Why it's enough to consider only such simple probabilities? Because on the first lectures, we saw that to guarantee that 2-point processes have the same distribution, we should check if they have common finite dimensional distributions, or they have the same Laplace functionals. But here it turns out that it's enough to know just such avoidance probabilities. It's very interesting and strong result. So before to formulate the statement, I want to give you the intuition in order to understand why is it true. And the idea is very simple if we consider countable state space. So consider countable state space X. So this means that we have a point process on some points, so we can denote them like 1, 2, 3, and so on. We can enumerate them. And now, in order to understand that avoidance probabilities uniquely define the distribution of a point process on this space, we just need to rewrite finite dimensional probabilities in terms of avoidance probabilities. So let us first give some annotation. So I will denote the avoidance probability. Or sometimes you can find in the literature avoidance function. This is a function of subsets like P0 of A. Okay, so this is by the definition the probability that process eta of A at subset A is equal to 0. So the probability that at point at subset A we have no points of a point process. And to know the finite dimensional distribution, let me recall finite dimensional distributions. We should know the probabilities of what sort. So we should take A1 for any integer k, and for every subsets A1 and so on, AK, and for every numbers N1 and so on, NK, the finite dimensional distribution, this is a probability that eta of A1 is equal to N1 and so on, eta of AK is equal to NK. So N also numbers with integer or 0 non-negative. Okay, so this is the finite dimensional distributions. So we prove the theorem on some first on the second lecture, I believe, that such finite dimensional distribution uniquely defines the distribution of a point process. So if we know that 2-point processes have the same probabilities of such form for each k, for each subset that then we understand that these points processes have the same distribution. So in order to understand the idea that avoidance probability uniquely define the distribution of a point process, we should rewrite the finite dimensional distributions in terms of avoidance probability. And for this case, it's enough to consider all subsets of the following form. So let us take just for k is equal to 1. So I will show you idea, and I believe you can do it later. So what are the subsets? So for k is equal to 1, subset I, now A, I can take the 1-point subset, right? And for this 1-point subset, I can write the probability of that eta of 1-point set is equal to 0. I can write it with this is itself avoidance probability, and for eta is equal to 1 is equal to 1 minus 0. So here 1 minus this. Right, so you can write down the probability of 1 point in such form. And then you can simply rewrite the probability of any for any subset of the form, like of the form if we have several points, like 1, I2, and so on, ik. And in order to rewrite it in the terms of this probability, we should take two-dimensional distributions. So let's take case equal to 2 and consider the following probabilities. That the probability that point process, for example, of I is equal to 0, eta is from J is equal to 0. So this is again P0 avoidance probability of such subset. And if I take I is equal to 1 eta of J is equal to 0, we can write it in terms of avoidance probabilities. Indeed, we can write here probability of J minus avoidance probability of the set I J. Right here, 0, 0. Yes, we have this. And the same probability of eta is equal to 1 if we have 2 points, heavy points in I and J. You just can write that this is 1 minus, and here you just can simply write this is 1 minus complement, and if you write complement of union, you will have here avoidance probability at point I minus avoidance probability at point J and minus avoidance probability at points I and J, and so on. So if you know all such probabilities, you can see that we can rewrite all sort of such probabilities in terms of avoidance probability, and such finite dimensional distributions you can write in terms 1 point subset. So this is just combinatorial calculations. So I think it's easy to understand that for such case, you can write down any probability of such form using avoidance probabilities of subsets. So from this and so on, from this we can understand the idea that if we know the distribution of so-called of empty subsets of a simple point process, then we can get the distribution of finite dimensional distributions. And here simplicity is very important, because actually when you know avoidance probability, you know just that. So here is important that the complement of empty of such event is that at this point I you have just 1 point. So this is just very important that you can have a complement of empty subset and you know that if you have 0 or 1 here at each point. So here the idea how we can get the result of the Renyi theorem, and now we will try to generalize this idea to quite general case. And to this aim, we should understand the idea what we will do to generalize it for more general case. So I will write the idea of how to generalize this approach. So we saw that we know the statement that we can characterize the distribution of a point of a simple point process if we know avoidance function, but only for of a countable space. So if we have arbitrary space, so let's consider for simplicity RD. We will consider on this case, but you will see what property of the space we use in order to generalize this approach. So this is a property of the space. So in the RD, how we can create the some countable, how we can create a point process with like on a countable space. We can consider the so-called like partitions of space RD, and we will see the point process not like a point process or the points in the R, but we will consider a point process on this partitions. So we will say that each subset has or does not have points in the cell. So I consider a cell like one point. This is the idea. And so here we will just create cells of the space, and then we can make partitions of dead partitions, and when we will do it more and more times, we can obtain a point process itself. So let's do this, and to give precise mathematical structures to such idea, let us define this set of partitions. And what kind of properties should we have in order to get the result? So let us give the definitions. As a definition, we will say that we have a dissecting system. Dissecting system of space X is the following. So we will have the sequence. We will denote it like tau. We have tau n of finite partitions so I have for any t, I have finite number of partitions like a and I, and I can takes value from 1 to some number nk, kn. So this number depends on n. N is from 1 to and so finite partitions of Borel subsets sets in space X is dissecting system if it satisfies the following properties. So the first property, so I said that this tau n is a partition. Partition property. So what does it mean? That the subsets for each n are not intersected. So we have for equal to I, and in the union A and J from 1 to Kn, we got space X itself. The second property is so-called nesting property. That any partition is a subpartition of the previous one. So this means that if I take the partition of the previous step and I intersect it with the set on the step n, J, this is exactly n J or empty set. So what does it mean? So if I have, this is the partitions of order n minus 1, then the next one we can just get of such forms. Yes, we just take the partition of a partition. So this is the nested property, and the last one, point separating property. This is very important. This means that we can separate any 2 points by a partition on some step. So this means that given points x and y in X, such that they are not equal, we can find an integer number that can depend on these points X and Y, such that if X belongs to A and I, then we will guarantee that Y does not belong to this set. And so this means that for any 2 points, X and Y, at some step we can find the partition where we can separate them, or such form. We can get different cells for each point. So knowing this, if we have such dissecting system for X, then we can create approximation of a point processes. So what is the idea? So how we can approximate a simple point process? So if we have dissecting system for dissecting system for space X, we can find for any X, we can find a sequence of subsets that depends on X. So they are from this dissecting system, such that in intersection we got just one point. So I think it's quite easy to understand on the example of the space RD. Yes, with RD, you just take the sets of the form like rectangulars of the form of such form k plus 1 over 2n and so on. So you can take rectangulars of such form k m r d d 2 to the power n kd plus 1. So please check that if you take such tau n of such forms, then you will have such a property. So now how I can apply this property for approximating a point process? Then for a measure, since this sequence is monotone sequence, this is by the property number 2 of nesting property, then we will have that measure of tau n of x just tends to mu of 1 point x. So this is how we can approximate the value of a measure by the value of measure of small partitions. And our next idea, how we can apply it for a simple point process. For simple point process, we know that this value of only 0 or 1. So mu Tn of x will tend to 0 or 1. So this is the idea that we will use to prove the next theorem. So let's formulate it. Theorem. This is due to Renyi, and later it was generalized by don't know how to pronounce. Okay, and the statement is the following: that the distribution of a simple, this is important, point process on space X with dissecting system tau is determined by the values of avoidance probabilities on the bounded subsets of the dissecting system tau. So here such a remark that just to apply this theorem, you should know that your state space X has dissecting system tau. So this is the main property. So this is the topological property of the space. So here, if to guarantee that such system exists, you just need to know some topological property of space X. So here that I say that you should know something about the state space X, because you should know that it there exists a dissecting system. And of course, you should know that your point process is a simple point process. So here the most important part, that the space should have the dissecting system, and the point process itself should be a simple point process. So now I assume that idea is understandable, because we already I already told about this. So let's just write a few lines to understand how we can create the approximation of a point process. Let me write it. We have a point process eta. So to prove, I will define a process zeta n of the following, using the following. So I will sum the subsets of partition of order n, and I just will calculate the number of non-empty subsets here. I from 1 to n. Okay. So as I drawn the picture before, if I have such a partition, something like that, and I take some subset A, and I have points then I just count the not the point itself. I just count the number of cells with which are non-empty. So I just count here. So on this picture, just is equal to 6. So it doesn't matter how many points we have here. We just want to be sure that this cells are non-empty. And now I want to write down. So now the point process n of a can be considered as a simple point process on space Xn, which have this. So we have subsets just itself a and 1, a and k. So we consider the elements of this space are these rectangulars, or the elements of descending subsets. So now the idea that we can write down the probability that of the distribution in terms of avoidance probabilities. So what are the probabilities that, for example, say zeta n of a is equal to 1. So how we can write it down? Not. We can take here arbitrary r, for example. Yes. So if we will know such probabilities in terms of avoidance probability for initial process, then we will get the distribution. And in order to write down such probabilities, let me define some notation. And the notation are the following. We will define so-called we will define the following difference operators. Define deltas at so for difference operator and it acts for function for functions which defined on subsets. So if I have subset A for any Borel subset, this difference operator delta acts on a function that and its value on subset B is equal to phi of B minus phi of B union A. So this is the definition. And In the same way, we can define the difference operator of order k minus 1 ak that acts on the function phi, and its value at subset b is equal to, we just take this value of delta a1 and so on a k minus 1 phi of b. So let's consider example that we will need just. So if we have a function phi that is avoidance probability, just eta of a is equal to 0. So we have some function that is defined on a subset. So then the action of a on this function phi of a of right here b is equal to difference operator. So this is just equal to the phi of b minus phi of b union a. This is by the definition, and we can rewrite it. So this is the probability of eta of b is equal to 0 minus probability of eta of b union a is equal to 0. And this is equal to probability that eta of a is bigger than 0. Just can write it. And eta of b is equal to 0. So you can see this. So why do I write down this quite different notation? This is because it's easy to check. So please check it by induction, because we already checked it for one order, that if I consider the difference operator of order k that acts on avoidance probability, then this is equal to probability that eta of a is non-empty for I is from 1 to k, and eta from b is equal to 0. So please check it, like this is not hard, this is exercise. And now let us come back here. We will see that we can derive these probabilities in terms of avoidance probability. So we just now we can just simply see that the probability that zeta n of a is equal to r. So we just need to take any r non-equal cells in the partition. So I take them r, not r, I1, IR. So I select R cells, and then I write the here action of difference operator of this for this subsets IR that acts on avoidance probability of subset A without this union. from 1 to R, A, and so please check this equality. This is very simple. You just need to know this one, and you substitute it here. Just you take all possible R non-empty cells in the partitions. So we can see so distribution of zeta n is defined through avoidance probability, and it's a little bit difficult formula, but you can have a joint distribution of also the joint distribution if you have just A1, A like M is defined through avoidance probabilities. So you can just it's a little bit difficult formula, so I didn't write it, but I suppose you understand the idea. And now the distribution of finite dimensional distributions of zeta n defined through avoidance probabilities, and now we use that a point process can be obtained as a limit of zeta n of A. This is just because we have monotonic sequence of zeta n, since n is monotonic. And the idea, like I said here, when we discuss that we have the convergence of values of subsets of dissecting partitions. So now here we can set since zeta n defined the distribution of zeta n defined through avoidance probability, then E, and the distribution of point process eta defined through avoidance probability. So I will write distribution of eta is defined in terms of zero. So this is mostly was the idea of the proof, because the statement quite difficult, because we should know the properties of the space, we should know the property of a point process itself, but I believe that most important to understand the idea here and to understand how to work with it. So this ends the proof, and here we will finish our lecture for today. Next lecture, we will apply this theorem to a Poisson point process, so it will be quite easy now. So if you have some questions, you can ask.